Very good evening, everyone. It's my real pleasure to be here. Thank you, Royal Society, for this wonderful event. So before coming here this evening, I was walking through the nearby park, and there's a beautiful statue of William Shakespeare. It got a very nice inscription. It says, "There's no darkness but our ignorance." So let's see how well that fit actually in today's black holes perspective. So it's a very beautiful journey of black holes. So I'll walk you through about that in the next 15 minutes. So before we start, let's do a thoughtful experiment. We take out a mobile phone and throw it up. So we know the harder we throw it, the higher it goes. But eventually it always falls back, right? But what if we could throw it with the speed little over than 11 kilometers per second? It will permanently leave the Earth's gravitational field, and it will never come back. And unfortunately, we would have to drive back home without our phone. So my apologies for making you do that. But this critical speed is known as the escape velocity. And it depends on how compact Earth is. So higher the compactness, the stronger the gravitational field, and larger the escape velocity. Now, immediately one can imagine an object which is so compact that the gravitational field becomes really intense that the escape velocity exceeds the speed of light. And now, not even light can come out of the object. And because of that, the object will look completely dark to an outside observer. This is not a new idea. Some of you might have already known this, that this idea of dark star was already there in the 18th century. But this is not very far from the current understanding of black holes. So the modern story begins with Einstein. In 1915, he wrote down his famous, beautiful set of equations to describe gravity. And within a year, the first mathematical solution to those equations were found, and it was a black hole solution. But it was so bizarre that time that even Einstein was never convinced that nature would ever form such weird object. And 50 years later, astronomers started finding evidence of these objects in the universe. And now, almost a century later, we can see them. We can photograph them. So it's a very incredible journey from being completely mathematical objects to astrophysical reality. So now let's do a little challenging exercise. Oops. Okay, this is challenging. Okay, perfect. Let's take our Earth and squeeze it with all forces. And keep squeezing it without changing its mass until it's become a size of a pebble or peanut. At that moment, the self-gravity of Earth will become so intense that it will overcome all other known forces, and Earth will start collapsing under its own gravity, and eventually everything will crush down to a single point and leaving nothing behind. This critical size where this runaway happens is known as the Schwarzschild radius. It's named after the same scientist who found the first black hole solution of Einstein equations. This black circle here, this marks the boundary of black hole. This is just a mathematical boundary, no surface. We can fall into the black hole, but there is no way to come out. The gravity is so strong that not our mobile phone, no planet, no rocket, and not even light can come out of this black hole. And in fact, most of the sufficiently massive stars in the universe, by the end of their life, they undergo a similar gravitational collapse process, and they end up as black holes. You might have noticed one thing, that the size of this black hole is dependent only on black hole mass. It's completely independent of Earth properties that we started with. And this makes black hole remarkably simple. Indeed, they are one of the most simplest astrophysical objects in the universe. We can describe any astrophysical black hole in the universe by only 3 numbers: how much mass they carry, how fast they are spinning, that's define the angular momentum, and how much electric charge they carry. These three numbers tell everything about a black hole. And this leads to a very weird concept. So if we start with two stars, which have these three numbers identical, same mass, same charge, same spin, but all other properties are completely different. They have different internal structure, different texture, different size, different shape, a different elemental composition, temperature profile, pressure profile, density profile, everything is different. And if you make them collapse under their own gravity, the resultant black hole will be completely identical to each other. So in this process, all that information about the original star is somehow lost. And all that information that we require to explain a star, what it is made of, what was the temperature, density profile and all, that has boiled down somehow to only these three numbers. This is very remarkable. And even the more interesting fact is, once a black hole is formed, no matter what we throw into the black hole, my laptop, guitar, even myself, all that information is lost forever. So no matter what contributed to the black hole formation at the first place, or what fall into the black hole remember nothing. So black holes are incredibly simple. They emit no light. They do everything to keep themselves hidden from the rest of the universe. And yet somehow they have become the celebrities in the universe. This is very interesting. Now this leads us to the important and obvious question that if black hole emit no light, how can we observe it? In astronomy, we often observe something invisible through their extreme gravitational effect on something that we can see. And this is how we study black holes, dark matter and dark energies. Dark matter and dark energy together make 95% of the universe, but we can't see them. We only see their observational and gravitational effects. What you are seeing here is matter swirling around a black hole and falling into it. When matter falls toward a black hole at relativistic speed, it gets squeezed. And the temperature rises up to 1 billion degree Kelvin, turning matter into plasma, very hot plasma. And that plasma starts radiating emission across the entire electromagnetic spectrum from highly energetic X-rays to radio waves. And this is the same light that we are seeing here. This is the same light that we are seeing here. This is the light produced by matter falling into the black hole, which you can see here. And there is a black hole at the center. If we zoom in very close to the black hole, this is what we will see. This bright orange light is the same light which is produced by the plasma before falling into the black hole. So some of the light managed to escape the black hole gravity and reaches the telescope. That's the light that we are seeing here, this orange light. But not all of the light actually can make it out to the telescope. Some couldn't escape, that fall into the black hole, and that's what makes this dark patch at the center. So what we are seeing here is the light which could manage to escape just outside of the black hole and could reach the telescope on Earth. And that missing light which couldn't escape, that's produced the black hole shadow. So this is the photograph of the light from just outside of the black hole. This is remarkable. We are seeing the very edge of the black hole is space-time, the very edge of the black hole horizon, the light coming from the horizon of the black hole. The ring here is made by the light which make orbits around black hole before escaping. And we can calculate the size of this ring. And it turns out that this is roughly 2.5 times bigger than the black hole itself. And this is purely because of the gravitational effect. In gravitational lensing, things appear bigger than their actual size. You might have noticed that the size of this ring is scaled with the black hole mass. So even if you take the supermassive black holes, which are millions and billions times bigger than our sun, even those black holes create a very small image on our sky. They make roughly the image of a supermassive black hole is roughly 15 million times smaller than a full moon image on a night sky. Now imagine, this is an incredibly small number. No conventional telescope on this planet can ever image such a small picture. Because to have that angular resolution, we need a telescope of disk roughly 10,000 kilometers in size, which is almost the same size as the Earth. So which is completely unfeasible. So this is exactly where this Event Horizon Telescope collaboration comes into the picture. This is a network of radio telescopes all around the Earth. It takes several radio telescopes around the planet and computationally connect them and create a single virtual Earth-sized telescope. And we get the enough angular resolution to take picture of supermassive black holes. I actually really find this interesting, that we are really fortunate because the size of Earth is of the right size that it provides us the enough angular resolution so we can image supermassive black hole. So nature is actually giving us opportunity to see black holes, but at the same time it's challenging us to create a telescope as big as the Earth. Some of you might have already seen these images somewhere in the media and in science magazines. These are the two supermassive iconic black hole images captured by Event Horizon Telescope in 2017. On the left, we have MET7 star, a supermassive black hole at the center of a nearby galaxy. This is one of the most massive black holes, roughly 6 billion solar masses. At the same time, it's really big. It's as big as our entire solar system. At the same time, it's really far away from us, fortunately, because light will take roughly 55 million years to reach us from the black hole. On the right, we have our own Sagittarius A star black hole. This is at the very center of our own Milky Way galaxy. This is relatively smaller than MET7, only 4.3 million solar masses, but it's still very far away from us. Light takes around 27,000 light years to reach us. Despite of all these differences in their masses, their size, their astrophysical environments, their images look quite similar to each other. They both have this dark center, which tells us that there is no light coming from this direction because that light has fallen into the black hole. They both have this bright orange ring, which is the light which managed to escape the black hole gravity and could reach the telescope on Earth. And this is remarkable because this also matches with the Einstein prediction of general relativity, even though he didn't believe in black holes at the first time. Now, with multi-year observation of the EHT, we can check the stability and consistency of these images. And it turns out that they are incredibly consistent in their sizes. All images have this dark center. All images have this bright emission ring of almost same size across all these different epochs of observations. Since the first observation in 2017, the Event Horizon Telescope collaboration is continuously upgrading its imaging capabilities, either by improving the technological facility of the existing radio telescope or adding new radio telescope to the existing array. But to improve the angular resolution, there is a challenge because of the limited size of Earth. We are already saturated by the maximum baseline on Earth because of the maximum diameter of Earth. And to improve the angular resolution further, we need to have a telescope in space. There are certain space missions which are underway, which will improve the angular resolution of this Event Horizon Telescope by a factor of 5. And with all those improvements, we will no longer have these fluffy and blurry images. We will have a very crisp, fine resolved image of a black hole, where we can see a very thin ring orbiting black hole, thin ring of light orbiting a black hole, and very prominent dark image at the center. That's a confirmation of a black hole horizon. Here comes the interesting part. What looked like a single ring is in fact multiple images are stacked out on top of each other. So black hole image is not a single image. It's a superposition of large number of images. And each image is produced by light which make additional orbit around black hole before escaping the black hole gravity. So the light which almost directly reach the telescope makes this n is equals to 0 image, which we call the direct image of black hole. And this is what the EHT is currently observing. If the light make 1/2 orbit around black hole before escaping to telescope, that's make n is equals to 1 image. That's we call the first order photon ring, and so on and so forth. Now in future, we will have enough angular resolution to see this n is equals to 1 image of a black hole, the first photon ring of a black hole. And that will be the confirmation that light orbits a black hole. The gravity of black hole is so strong that it forces light to make orbit around it. And not only that, because now light is spending substantial amount of time orbiting black hole, it will have information of the black hole space-time, those 3 numbers, and using the observation of this black hole photon ring, we can actually extract or we can have some information about the black hole magic 3 numbers. So this is something that we expect to see in the next couple of years. So for a very long time, black holes were just mathematical objects, some solution of some field equations. Today we have their images, we can have their photographs. Tomorrow we will see light orbiting black holes and even movies of black holes. Well, thank you so much.
Thank you so much. Does anyone have any questions for Rahul? We've got one question here. We've got time for a couple.
Thank you for a very interesting talk. I just wondered if there's any theories behind why there are black holes in the center of galaxies. And also, I mean, I know there must be some that aren't centers of galaxies, but why are there, you mentioned 2 that are centers of galaxies. And also, is the black hole the same size as the star was previously?
Okay, this is actually a very interesting question. And I'll give you a very honest answer. We don't know. We know that there are supermassive black holes at the center of almost every galaxy, but that's the quest, that why do we have black holes there? I think there are some models, but we don't have very convincing theory for that. The one reason is because we need something really strong gravitational pull to hold the galaxy together. And that, I think, is because of the supermassive black holes, because they are really, really big. The second theory is that some of these supermassive black holes, they feed the galaxy. They have relativistic jet coming out of them. And that leads to the galaxy formation. But still, there are some missing gaps. To answer your second question, the resultant black hole doesn't have to be of the same size of the star. Actually, it never is. For example, if we have to take the Earth and we collapse it, the final black hole size will be of the size of a pebble, like few millimeter. For Sun, which has 1 million kilometers in size, the final black hole size will be only 3 kilometers. It's a huge difference. Thank you.
Hi, thanks for the talk. All your photos of black holes are shown with a ring face onto us. Are there none where we see them edge on? Why do we always see the ring as a donut and not from the side?
Interesting. Again, we are really fortunate for that, because so what's really happening here, so there are supermassive black holes and they are spinning. And because of their spinning, there is a sense of direction. We can define the inclination angle. And for the M87 black hole, the inclination angle is very small. That's why actually we are not seeing them edge on. For Sagittarius star, the inclination angle is not very well known yet. But there are simulations, if we look at different inclination, there are some differences in the brightness.
Possibly a simple question, but I'm curious. In the images you've shown today, there are some areas of light that are so much brighter than the rest. Is there a hypothesis as to what causes that?
Well, this is a very interesting question. And so let's see here. So what's really happening here, what we are seeing basically is the light produced by the relativistic plasma orbiting black hole. And it's a simple Doppler effect that when the light is produced by something which is moving towards us, it will appear brighter. And the light produced by the plasma which is moving away from us, it will appear dimmer. And that actually tells us that the lower part is brighter. So the plasma in the bottom part of the black hole is moving towards us, and the matter in the top part is moving away from us. So this tells us that the plasma is moving at the relativistic speed around black hole, and black hole is indeed spinning. But how fast it is spinning, we don't know.
Okay, we've got time for one last question. Thank you.
You mentioned that black holes are quite simple objects. They can be measured by their mass, charge, and angular momentum. Could there be something that we don't know yet, maybe their internal structure or something that can't be observed from outside, but this might still create some difference between them?
Actually, I had a change of thought just 1 hour ago after reading that Shakespeare quote. The darkness is our ignorance. And I totally agree with you. Maybe there is something which we are ignoring. But there are actually some models which are alternative to black holes. But currently, the observations are actually strongly supporting the black hole confirmation. Thank you.